So in this video we are going to discuss, not in full details, but in some kind of hand-wavy way of how to apply EM algorithm to the probabilistic principal component analysis. So let's look at the E step first. On the E step we have to find the we have to set Q to be the posterior distribution on our latent variable t. So Ti given xi and theta. And in general, it's proportional to the joint distribution, so to the x given t times p of t, divided by some normalization constant. And in general, this normalization constant is hard to compute because it's an integral of with respect to xi. But in this case, it will not cause us any trouble because we we're able to compute everything analytically, because everything is normal, everything is conjugate, and this thing will also be normal. And you can look up the formulas for mu tilde in Wikipedia. So E step is easy. We can easily find everything analytically. What about the M step? Well, on the M step, we're trying to maximize the expected value of the logarithm of the joint distribution. So we can rewrite this formula as we can swap summation and expected value, and we'll get some with respect to objects in the dataset, expected value with respect to Q of Ti, of logarithm of our P of x given Ti times P of Ti. What it is? Well, P of x given Ti is some normalization times normal distribution, which is something under exponent. And P of Ti is also some normalization times exponent and some normal distribution. So first of all, we can notice that since logarithm of product is sum of logarithms, and since the normalization constant z doesn't depend on Ti at all, then we can rewrite it as follows. So we don't have to find the expected value of logarithm of 1 divided by z, because it doesn't depend on Ti, and its expected value just equals to the logarithm of 1 divided by z itself, right? Then the second term here is expected value of logarithm of some exponents. And the second exponent is the prior. It's minus Ti squared by 2, divided by 2, in the one-dimensional case, so if Ti is one-dimensional. And the first exponent is some quadratic function of Ti, which basically measures the distance between the actual point xi and the projection of the Ti into two-dimensional space, or multi-dimensional space in general. So this thing, if you look carefully at it, it's some quadratic function with respect to Ti. So logarithm of this exponent products is a quadratic function with respect to Ti. And in general, computing the expected value here can be hard. But in practice, Q is normal distribution, and computing expected value of some quadratic function with respect to a normal distribution is not that hard. So we can easily analytically compute this expected value, and then what is left is some actually concave function with respect to parameters. Because from this expected value of Ti or expected value of Ti squared, we will get some just constant with respect to parameters, and we'll have to maximize it with respect to parameters theta. And this can be done analytically. So we can just compute the gradient and set it to 0 and compute the optimal theta. So this was kind of hand-wavy explanation why EM is not hard in this probabilistic PCA case. And as we have already discussed, this probabilistic formulation of PCA allows you to do a few cool things. So first of all, you can extend your model to be able to handle missing data by just calling these missing values to be latent variables, and then applying this EM. And you have to just extend this EM a little bit to handle these new latent variables. Well, second of all, it gives you a straightforward way to build an iterative scheme to compute the PCA. So even if you don't have missing values, in some cases, if you have, like, for example, really high dimensional space originally, and you want to project into a really small dimensional space, then PCA can be slow. And it can be faster to use some iterative scheme. And of course, there are several iterative schemes for doing PCA from linear algebra community. But it turns out that, well, you have to know linear algebra to derive them. You have to think carefully and it's not that straightforward. But expectation maximization just gave you a straightforward way to compute some iterative scheme, which can be more efficient than the original PCA in some cases, like when you have much higher dimensionality of the original data than the lower dimensional subspace. So you don't have to think that much. You can just apply the EM and see what happens. Another cool feature of probabilistic PCA is now that you have this baseline probabilistic model, you can do a mixture of them. If the flexibility of your original PCA is not enough. So you can easily extend your model to be more flexible, and then everything is not analytical anymore, but you can still apply EM and compute some solutions, so to train the model. And finally, and it sometimes helps with tuning hyperparameters to treat everything probabilistically, because it allows you to tune the hyperparameters with by tracking the log likelihood on the validation set, which is sometimes not feasible with non-probabilistic models with unsupervised datasets. And for example, you can choose between using the full covariance matrix sigma and using just diagonal approximation of that. So they have much different, very different number of parameters. And you can choose between these two by just considering the log likelihood on the validation set. And in principle, you can improve your solution to this unsupervised problem.